All right, we're going to learn why enamines were so important in chapter 16. It's so we can use them now. Chapter 16, we learned that aldehydes and ketones will react with secondary amines to make enamines. And here the ratio will be pretty close to 50-50 because both alkenes have the same substitution. That is to say, they have 2 carbon groups and they have a nitrogen. So 50-50, and let's get busy. We're going to have to go red first, blue second. We don't have to. It makes life a little better. We got a lone pair on our nitrogen. Scratching off the H here and putting it back on as with its bond showing. Pushy lone pair attacks the carbonyl, pi breaks. Lone pair on the the former carbonyl, which is now an O minus, is going to grab the H. Second step. Can't reach the H because the intermediate would have a 4 carbon ring transition state. So that's an intermol. Intermol. There you go. That arrow has to be between 2 different molecules. And that will generate a species that looks like this. Gonna need 2 copies. Got an O, got an ethyl, and we got an H on there. We got an N. Okay, we'll put it in green. N got its lone pair back, ready to do its pushiness again. We don't need 2 copies just yet. We need 2 copies after we push off the leaving group. Hydroxide, not normally a good leaving group. Nitrogen, fully capable of pushing it off. Need 2 copies of this. Think it'll let me? I got a free arrow. That arrow's going to become an equal sign, isn't it? Well, how sly is that? Okay. I think I see the 2 products. Product to the left, this H has to go. Product to the right, this H has to go. What's going to grab it? OH minus each time. Yeah, I can write OH minus black here. And HO minus. Grab H, sigma becomes pi, resonate to neutralize the nitrogen. Grab H, sigma becomes pi, resonate to neutralize the nitrogen. And we got enolate on the left from the one on the left. Enolate on the right from the one on the right. And there you go. Enamines behave like enolates. That's why we're studying them here in the enolate chapter. Their behavior is the same. You can do aldols and clasins with them. So let's remind ourselves, how do you know when you have an aldol and when you have a clasin? It doesn't have to do with the attacker. It has to do with what gets attacked. And the thing being attacked here is the ketone with the 1 above it. When enolates attack aldehydes and ketones, we call it an aldol reaction. In our next activity, we'll have the other enamine, which doesn't get to do anything in this activity, but on our next one, it starts the activity and it's going to do a Claisen because it's going to attack an ester. Wait for activity 5. I know you can't wait. We're almost done this one. Lone pair resonates down. That's what makes enamines like enolates. Pushy lone pair resonates down to be a nucleophile on carbon. Carbon attacks carbonyl. You get an O-. I have a small correction and addition here. Please add a 2 over here. I wanted to put it there, I just forgot. And please add ethanol here. It wasn't there, but I need it there. HOET. Because that's where the proton comes from. For next step, which is right here. You ready? Next step right here. And that combination becomes what's drawn. No intermediates. I love this. The combination of those blue and red arrows gets us from A to B. So I'm off the hook for letting the other mechanisms run over to the right side here. What's going on here? There's quite a bit going on here. I clearly see the alkene happening like the aldols usually do to make aldol reaction product. Can I call this an aldol reaction product? And this is the ACP plus hydrolysis. Oh, hydrolysis. It's hydrolysis. Using water, I break the molecule apart. And if you're curious about the other product, here it is. There's the other product. Let's get busy. Let's do the making of the pi bond first. Protonate to make a better leaving group using your catalyst. And then the sulfate ion you just generated. Can do the elimination for you. Remember, it's always alpha H. It's the second time you've hit that alpha position. Sigma becomes pi, leaving group leaves. And I like this pink arrow. Let's carry on that theme here. You've got your isopropylidine group here. What did he just say? Don't worry about it. Dimethylmethylene, you can call it that, or isopropylidine. That's taken care of. Hydrolysis, yeah. Finally get to circle something, call it R. Hydrolysis, let's get busy. Water's got to be used for sure. In fact, let's be smart about things. HOH. Step 1, attack. Neutralize the nitrogen. Step 2, we got hydrogen sulfate and sulfuric acid. I need some kind of base. I need the sulfate ion. Step 2, neutralize your oxonium. We're going to make an aminol. Aminol. I know you want to say animal, but it's not that animal. Let's be smart about things and see if we can get to the final result. Clearly, the O has to lose its H. I wouldn't be doing that right away. Nitrogen clearly needs to get bond to H. Definitely need that to make it a better leaving group. Don't want N minus leaving. So HCl number 1 is here. It'll definitely be creating a Cl minus.
Where did you get the HCl?
From my imagination, apparently. So yes, I had a good question. Yes, from where did you get the HCl? Very good question. I got it from the wrong strong acid. I'm so used to using HCl, I caught myself, didn't I? Sulfuric acid does whatever HCl does, right? And of course, the conjugate's going to be OSO3H negative, which we just made. Yeah. I think that's going to strip the hydroxyl H off, even though pKa says not favorable. When we get to our final product, it is. And it looks like the nitrogen needs a second H. Can we show that? Where's it going to get it from? Here's a hint. You need lots of sulfuric acid for this one. So feel free to use it as many times as you want. Here's another sulfuric acid, same arrow. And I'm just going to use it as part of the blue arrows. Say, as it's leaving, it has to protonate. Because as it's leaving as an amine, what's the most important thing about amines? No, that's not what he said before. What's the most important thing about amines? Not so long ago. Chem 241 talked about amines and their importance in biology and biochemistry. The most important thing is their bases. Now they remember. And amine is going to definitely react with a strong acid if it's a base. That's what's going on. So protonate and then what looks like an elimination here. And that's the end of the story for this. And how we show that's the end of the story. Wow. You know, the pink arrow. There's the whole deal. And we'll see ya.